Hello, welcome to the lecture on the value of accuracy, and thank you for joining me on the path to sustainability. This lecture is broken up into 4 videos. In this first video, we'll discuss a systems engineering topic applicable to many systems, specifically how quantifying the value of a design variable can help us make wise trade-offs across the subsystems of a product. In the second video, we'll apply that general principle to BMS cell voltage measurement. In the third video, we'll dive deep into BMS chip datasheets. And in the fourth video, we'll discuss the value of accuracy in battery current measurement. Systems engineering entails making trade-offs across different systems, components, or subcomponents. Weight is an example of a mechanical trade-off. Should I spend more money for a lighter weight vehicle chassis? Should I spend more for a lighter weight battery? Should I spend more for lighter bolts? We have similar trade-offs in the electrical domain. Should we spend more money on a more efficient microcontroller for the vehicle computer? And for the battery management system? And for the infotainment? Should we spend more to reduce the quiescent current of the windshield wiper controller? You can imagine how a different engineering team may be responsible for each of these subcomponents. How can we make sure that each team uses the same optimization criterion to optimize weight versus cost, or energy versus cost? One approach, a traditional one, is to have a systems engineer or systems architect allocate how much of the total weight and cost and power budget goes to each component, and then to each subcomponent. An alternative approach is to distill certain system-wide targets like weight and power into a common target. Dollars are a good one. You can do some system analysis to calculate the product level cost in dollars per kilogram for every additional kilogram added to the product, or for energy usage in dollars per amp or dollars per watt. Let's do an example. As an example, let's calculate the dollars per kilogram value for an electric vehicle. If we build a heavier vehicle, to guarantee a target range, we need a larger battery. The heavier weight may necessitate a stronger chassis, stronger brakes, and so on. A heavier vehicle costs more to build. We can quantify all these costs. For our example, let's focus just on battery cost. As we increase the vehicle weight, if we want to maintain a constant range, we need to increase the size of the battery. In the real world, you do some experiments or simulations to figure out the relationship between weight and range. In this example, let's assume that through rigorous analysis, we found that a 10% weight reduction gives us a 9% range improvement. Let's assume that the vehicle battery costs $15,000, and let's assume that the vehicle weighs 1,800 kilograms. We can put those numbers together into a metric. Our metric tells us the value of weight reduction. If I can spend less than $7.50 to remove 1 kilogram, it's worth doing. Let's apply our $7.50 per kilogram to some totally made-up decisions. Pretend you are the bolt engineer. You've found 2 bolts that meet all the other requirements and differ only in price and weight. You can pay an extra 3 cents to reduce the weight by 2 grams. Should you do it? We can do some math. We can calculate that 3 cents divided by 2 grams is $15 per kilogram. This weight optimization is more expensive than our system target. So, buy the heavier, less expensive bolt. Now, pretend you're a manufacturing engineer. You're responsible for stamping some part and realize that you can tweak the stamping process to reduce weight. Unfortunately, 1 in 1,000 parts made in this new process don't come out quite right. You expect more scrap. Should you change the manufacturing process? Again, we can do the math. The numerator accounts for a 0.1% yield loss on a $20 part. The denominator accounts for the 4-gram weight reduction. This process change costs $5 per kilogram, less than our system target, so we should do it. In this case, increasing the subcomponent cost leads to product-level savings. These fictional examples illustrate how Our dollars per kilogram metric allows the bolt engineer and the stamping engineer to optimize to the same criterion. Two people working on different teams can value the weight versus cost trade-off in the same way. Pretty cool, huh? This is the end of video 1. Please continue this lecture in video 2.